Today we will start with a new part of the course. This is part 2, and the main topic now is amplifier frequency response. So what do we mean by amplifier frequency response? The observation here is that if you take an amplifier and you apply a certain input, the amplifier has a certain gain, and the output will be this gain times the input. In this equation, in this relationship, there's really no mention of what is the frequency of the input or the frequencies of the input. If we assume for now that we have just a sine wave at the input, it will have a single frequency component, and the frequency at which this signal is oscillating plays no role, at least in this equation, that VO is gain times VI. The frequency does not appear anywhere. But the observation is that if we change the frequency and we measure the gain, or we look at the output, we find that as we change the frequency, as we increase the frequency, the output changes. And it is not just the frequency in the output. Of course, the frequency in the output will change with the frequency in the input. If the input frequency is 1000 hertz, the frequency of the output should be 1000 hertz. And if the input frequency is 10,000 hertz, then the output frequency should be 10,000 hertz. Here I'm assuming a linear amplifier, which is the case in our study. So if I change the frequency from 1000 to 10,000 to 100,000, so that's 100 kilohertz, and then 1 megahertz, 10 megahertz, what happens in reality is that the output signal, which will be at the same frequency as the input signal, will change in amplitude and also in phase angle as I change the frequency. This is something that we have not discussed so far, and this is new. And this is what we want to study in this part of the course. So how does the amplitude and the phase of the output signal change, not with the amplitude and the phase of the input, but with the frequency of the input? So this is what we call the frequency response. Now, why did we ignore this so far? Because at low frequency, there's really nothing in the circuit that is affected by frequency. If we look at the circuit itself, we have the resistors, we have the transistors, sometimes diodes, and we saw capacitors and very rarely inductors. And at low frequency, close to DC, we said that the capacitors would be open circuits, and also the inductors would be short circuits, and we eliminate them. And therefore, at low frequency, we have nothing that is affected by frequency. The resistor, a certain resistor has a resistance that does not change with frequency. The MOSFET models that we're familiar with don't have components that change with frequency. But in fact, if we consider capacitor impedance, and we will focus on capacitors in particular, the capacitor impedance is ZC of S in the S domain. It's 1 over SC. And in the J omega domain, it is minus J over omega C. So when omega is 0 or close to 0, this impedance is very, very large. It's infinite. It approaches infinity. So as in the low frequency domain that's close to DC, the impedance of a capacitor is infinite. And that's why we replace a capacitor by an open circuit, because its impedance is infinite. That's an open circuit. Z, magnitude of Z is 1 over omega C. As omega goes to 0, Z goes to infinity. So the capacitor is an open circuit. But look at the formula, and here you see omega. So now if I change omega, the impedance will change with it. And if omega becomes large, the impedance becomes small. And not just small, but also it's a complex impedance. So it's a complex number. It has a magnitude and a phase angle. Now the phase angle happens to be fixed because it's pure imaginary. But the magnitude is 1 over omega C. And as omega increases, the magnitude decreases. So here we have our starting point to understand why the amplifier produces an output magnitude and phase angle that vary with frequency. Maybe there are capacitors in there and their impedances are changing with frequency. And that's really the reason, because there are capacitors in the circuit, their impedances are changing with frequency. And as the impedance changes with frequency, everything in the circuit is now changing. So we get an amplitude and a phase angle for the output that also vary with frequency. So now our study here is about this frequency response. And if the input is a sine wave, say sine omega t, for simplicity, I will take the amplitude of the input to be 1. The output would be a sine omega t plus phi in general. And a over 1 would be the gain. And phi, so far in 310 and 311, we saw that the output is inverted. So phi is like 180 degrees. There's a 180 degrees phase difference between the output and the input. So this is what we know, that A would be gain when the input amplitude is 1, and phi is 180 or maybe 0, so 0 or 180. But in reality, it's more complicated than that. And A is really a function of omega. So it's an A of omega. And phi is also a phi of omega. So it's not 0 or 180. It may be between 0 and 180, varying with omega. And A may be the low frequency gain, the one that we know how to calculate so far. But it may change as we change omega. It won't be constant. So where do these capacitors come from? We said that maybe there are capacitors in the circuit, and then the capacitors will have an impedance that changes with the frequency, and the circuit characteristics would change with the frequency. Okay, but where do they come from? We don't add them to the circuit ourselves, maybe, except for some maybe DC coupling capacitors or bypass capacitors. But what if there are no capacitors that we added ourselves? Well, there would still be capacitors. And the reason is the MOSFET small signal model at high frequency, so when omega becomes large, so away from DC, includes capacitors inside the MOSFET. So there are 3 capacitors inside the MOSFET due to capacitive effects inside the device itself. So inside the device, due to the way it's fabricated, there are 3 capacitors there. They're very, very small, very tiny capacitors. And at DC, we can remove them. We remove them, and their impedance is very, very large. So we never care about them. We never worry about them when we have low frequencies. But if I want to consider frequency, I need to add these capacitors because their impedance would change with frequency. So I have 3 of them in the MOSFET. And again, I have to use MOSFETs. If I have an amplifier that uses MOSFETs and the MOSFETs are amplifying, the MOSFET will come with these capacitors inside the MOSFET. and they're part of the model of the MOSFET. And they are there not because someone added them on purpose. They are there because of the way the device is fabricated and manufactured. When you have two conducting plates that are close to each other, then that creates a capacitive effect. If you have a p-n junction, that creates a capacitive effect. And we have such things in the MOSFET. We have p-n junctions and we have the gate plate. So yes, there are places where we would have capacitive effects. And this is how we model them with these three capacitors. If you open circuit the capacitors, what happens? You get this. And that's no surprise, because what is this? This is exactly the MOSFET small signal model that we're familiar with, the one that we use in our amplifier analysis, GM, VGS, and RO. But in general, in addition to GM, VGS, to the control source and the resistor RO, there are three capacitors: CGD between gate and drain, CGS between gate and source, and this CDB, but B is the bulk or the body or the substrate, and in general, we'll assume that the B and the S are shorted together, so CDB appears also between D and S. So between G and D, I have a capacitor CGD. Between G and S, I have a capacitor CGS. Between D and B, I have a capacitor CDB, which would be between D and S in most cases when B, the body, and the source are shorted together. So these three capacitors are there, and of course they will change the characteristics of the amplifier now. And we'll see how in this part of the course. Same for the bipolar transistor. Also, there are two capacitors there, and they're C pi between base and emitter, and C mu. So C pi is in parallel with R pi, and maybe that's why it's called C pi. And C mu is between the base and the collector. So two capacitors. There is a third capacitor that we generally won't include in this course. So again, two capacitors. Whenever we have a BJT, there are also two capacitors that come with it. They're very small, very tiny, at low frequency, close to DC. You can safely ignore them and remove them. But if I'm doing a frequency response study, they're there, they would affect my amplifier, and I have to study how they would affect the amplifier. And as a side note, we introduce a quantity called unit gain frequency, which you may see in some exercises or some problems. And this is called, this is FT, referred to as F sub capital T. It's called the unit gain frequency. And it's related to, in the case of MOSFET, it's related to CGS and CGD and also GM. So FT is GM over 2 pi CGS plus CGD. In the case of BJT, it is GM over 2 pi C pi plus C mu. So why do we mention this? Because if I'm given CGS and FT, the formula here would allow me to find CGD if I need it in my circuit analysis. Same for the BJT. If I'm given C pi and FT, I can tell what C mu is, assuming that I know what GM is. So that was a side note just to introduce this quantity called unity gain frequency, FT, as you may use it sometimes to solve some problems. All right, so now we know that for the MOSFET, I have the three capacitors, they're there. For the BJT, I have the two capacitors, they're there, and they would affect my amplifier response. So let's start with a very simple case. Just take a very simple amplifier with a source and a load. So here's my source. Okay, signal source, not MOSFET source, signal source. VS and RS, so that's the Thevenin equivalent of a signal source. The amplifier, has an input and an output, and this is the load, and we're modeling the load as simply a resistor RL. So this is a regular voltage amplifier, and I want to just analyze the effect. If I have just one capacitor in the circuit, what happens? Does the output really change with frequency because of that one capacitor that I add? Let's see. Here's the model of the amplifier. So I have this amplifier, and now I replace it with its model, and the model consists of an input resistance, Ri, an output resistance, Ro, and a controlled voltage source, AVOVI, where AVO is the open circuit voltage gain. So inside the blue rectangle, I'm not showing all the details of the amplifier to keep the analysis simple. I'm just showing the model of the amplifier: input resistance, output resistance, controlled voltage source. So now I will add one capacitor, and we will study the effect of just this one capacitor on the gain. So let's add a capacitor here in parallel with Ri, Ci. Because in the case of MOSFET and in the case of BJT, there is a capacitor that appears between gate and source, or between base and emitter. And for the amplifiers we studied, this is where the input was, between B and E, or between G and S. So that's why it's useful to study the effect of such a capacitor that appears at the input in parallel with the input resistance. So what does this Ci do? Let's see. Now, I'll use some numerical values just to illustrate, and I will try to find VO over VS, so the overall gain. What is VO over VS? And then plot the magnitude response and the phase response. These are called the Bode plots. And then find the voltage VO of T. So the output voltage is a function of time, A sine omega T. What is A? What is omega? What is phi? A sine omega T plus phi. When the input, or the source, excuse me, is 0.1 sine 10 to the power n T, with n 2, 5, 6, and 8. So if the source is 0.1 sine 100 T, what is the output of the source is 0.1 sine 100,000 T. And if the source is 0.1 sine 1 million T, and if the source is 0.1 sine 100 million T, what will be the output? Okay, this is actually a circuit, not too complicated. I want to find VO over VS. It's two parts. So let's start with the input. This is the input side. I want to find first VI as a function of VS. Now I will consider R and Ci. I will consider this combination to be an impedance. So I will call this combination of Ri and Ci Zi. So now Zi and Rs form what we call a voltage divider. So here's Vs, here's Rs, and here's Zi. Zi is an impedance, which is the parallel combination of Ri and Ci. This is Vs, and this is Vi across Zi. So that's a voltage divider. This is a very useful formula when I have such a structure. I want the voltage across one of two impedances in series, it will be the value of the impedance times the sum of the two, divide by the sum of the two times the source. So VI would be VS times ZI over ZI plus RS, voltage divider formula. Okay, what is ZI? Well, ZI is the parallel combination of RI and CI. So 1 over ZI is 1 over RI plus SCI. That's a parallel impedance formula. So that's YI. We call this YI. We can refer to this as admittance. So instead of writing the voltage divider formula as ZI over ZI plus RS, I can write it in terms of YI. So this is 1 over YI. And this is 1 over YI. And then you get 1 over 1 plus RS times YI. And that's YI. And this is what we get here. So VI is VS times 1 over 1 plus RS into YI, 1 over RI plus SCI. So now we start to see how the capacitor entered in the equation. But I don't want VI, just VI. I'm after VO. Okay, so again, this is the same formula. What about VO? At the output, I also have a voltage divider. So here at the output, this is also a voltage divider between RL and RO. So VO across RL is RL over RL plus RO times this AVO VI. So VO is AVO VI times RL over RL plus RO. So from this equation, I have VI over VS, and from this equation, I have VO over VI. So how can I find VO over VS? I'll take this, multiply them, and I get VO over VS. So that's VO over VS. And here it is. So the first part here is from the output voltage divider. The second part is from the input voltage divider. This is of the form K over 1 plus S over omega 0. It looks more complicated than that, but it's really just that. K would be all of this. AVO is just a number. There's no S, there's no omega, J omega. This is just a real number. RL and RO are real numbers. RI and RS are real numbers. So all of that, I can call it K, and K would be a real number. And this quantity, CI times the parallel combination of RI and RS, I want to call it 1 over omega 0. If I do that, the whole thing becomes K over 1 plus S over omega 0. And this is the overall gain of this amplifier from the output to the source, T of S. Or sometimes you call this the transfer function. Why is this form interesting? Why did I write the transfer function in this form? This is something that we're supposed to be very familiar with. This is called the low pass single time constant transfer function. Low pass single time constant transfer function. Another term for this is first order low pass filter. if you build, if you try to have the simplest form, the first order, simplest form for a low pass filter, what would be its transfer function? It will be something like K over 1 plus S over omega 0. So this is the simplest form of a low pass filter. So this amplifier is amplifying, providing gain, but also acting as a low pass filter. What does the low pass filter do? The low pass filter filters, right? It's a filter. And the low pass. So the low frequencies pass. It amplifies the low frequencies in a good way. But then it's a filter. If the low pass, the high don't. The high frequencies will not pass. But it's a first order. So it's not a great filter, a very sharp filter. It's a first order. So it will not block high frequencies completely. It will just reduce the gain at high frequencies. So this is the relationship now between what we know about filters and what we know about amplifiers. This amplifier, by the addition of this capacitor Ci, just one capacitor, will act not just as a regular amplifier with a gain that is constant and the same for all frequencies. It will have some gain, and the gain here is, I'm calling it K at low frequencies, but then it will start to filter. So the low pass and the high don't pass. So the higher frequencies will not get as much gain, will not get as amplified as the low frequencies. So this K is really the low frequency gain of the amplifier. What do we call omega 0? Omega 0 is a very special frequency. Omega 0 is called the 3 dB frequency. And now we will learn why it's called the 3 dB frequency. And the numerical values for K and omega 0 for this particular amplifier with the numerical values that we showed are 100. So this is the low frequency gain. It's a decent amplifier. It has a gain of 100 for low frequencies. But then there is something that we are referring to as 3 dB frequency. So like some important frequency there, which is 1 million radians per second. At 10 to the 6 radians per second, there is something important that happens. And we will see next what is this something that's important that's happening. Before I continue, let's see if there are any questions. Please raise your hand or type in the chat window if you have any questions. Okay, so let's review this low pass single time constant transfer function, or the transfer function of a first order low pass filter. This is how it looks like: K over 1 plus S over omega 0. And the low frequency gain is K. And the upper 3 dB frequency is omega 0. So we call it upper 3 dB frequency. There are other terms that we may use and you may see. Omega 0 is also called the corner frequency, or the cut-off frequency, or the half power frequency, or the critical frequency. It has several names, but they all refer to this omega 0. So it's the important frequency for the transfer function for the low pass filter. All right. So what happens at omega 0, after omega 0? Here's what happens. When the frequency exceeds omega 0, I know omega 0, in this example, it's 1 million radians per second. So when I know what it is, here's what I can say. That if the frequency at the input exceeds omega 0 and becomes larger, maybe much larger, quite larger than omega 0, then the gain will drop. So that's this part I know because it's a low pass transfer function. But now I can tell more because of the form of the transfer function. If the frequency of the input is much bigger than omega 0, the gain will drop at a rate of -20 dB per decade. -20 dB, we know the dB. What is a decade? A decade is a 10 times change or a 10 times increase in frequency. So if the frequency increases 10 times and the frequency is larger or much larger than omega 0, the gain will drop 10 times. So a 10 times increase in frequency would correspond to a 10 times drop in gain. So back to our example, let's say I have an omega, which is 5 million. 5 million, not too much larger than omega 0. Omega 0 is 1 million. 5 million. And the gain there is, let's say, 80 volt per volt. This formula, -20 dB per decade, would tell me that if the frequency increases from 5 million radians per second to 50 million radians per second, what do we call this? We call this a decade, because the frequency increased 10 times from 5 million to 50 million. This is a decade, a ratio of 10. The -20 dB per decade tell me that if the frequency increased from 5 to 50 million radians per second, the gain will drop by also a factor of 10. And if it was 80 volt per volt at 5 million radians per second, at 50 million, it will become 80 divided by 10, 8 volt per volt. So from 5 to 50, this is a decade in frequency. And it will, because this range of frequencies is larger or much larger than omega 0, the gain will drop by a factor of 10. So it will go down from, say, 80 to 8. This is the meaning of -20 dB per decade. And dB, a 10 times drop in gain, is a change of -20 dB. And in frequency, a 10 times increase in frequency is called a decade. So -20 dB per decade means if the frequency increases by a factor of 10 times, the gain drops by a factor of 10. But with a condition. This doesn't apply for all frequencies. Applies if we're looking at frequencies that are much larger than omega 0. So that's pretty dramatic, right? I mean, the gain was 100, and at 5 million, it drops already to 80. And then at 50 million, whoa, it's 8. So this amplifier that had a gain of 100, and it was very nice gain, very good amplification. If the frequency is 50 million radians per second, then this gain of 100 is now 8. If the frequency increases to 500, the gain drops below 1. So what happens to the amplifier is it's no longer amplifying. It's not even amplifying anything. The output is now less than the input. So this is what we want to study in detail, really. And a nice way to study this in detail is by doing the Bode plots. The Bode plot is a nice graphical representation of the transfer function. So there are two types of Bode plots. There is the magnitude plot and there is the phase plot. Now, when I have a transfer function like the one on the previous slide, k over 1 plus s over omega 0, when I want to study the effect of omega on this, what I do is I take the s and replace it by j omega. And then this becomes a t of j omega. This becomes a complex number, k over 1 plus j omega over omega 0. That's a complex number. And we know that for complex numbers, they have a magnitude and a phase angle. So the Bode plot for magnitude is a plot of the magnitude of t. And the Bode plot for phase is a plot of the phase of t. T is the complex number. And so that's on the y-axis. On the x-axis, it's omega. But the Bode plot is special in that the y-axis for magnitude is in dB. So it's not in volt per volt for voltage gain. It has to be in dB. And the x-axis is log scale also. So I don't show omega as 1, 2, 3. I show omega as 1, 10, 100. So here's the Bode plot for magnitude. And the magnitude is the magnitude of t. So 20 log magnitude of t of j omega, because I want it to be in dB. So this is the units on the y-axis are dB. So 20 log magnitude of t of j omega. These are the units on the y-axis. On the x-axis, I have omega in log scale. Log scale means that I don't go 0.1, I don't go 1, 2, 3. I go 1 omega 0, 10 omega 0, 100 omega 0, and so on. So the step on the x-axis, the step is a times 10. Times 10. This is what we call the decade, a times 10, times 10. And when I do this, it's still omega. The units here are still units of omega. Omega 0 and radius per second. 10 omega 0 is radius per second, and so on. But we say that on the x-axis, I have omega in log scale. So if omega on the x-axis is in log scale, and on the y-axis, I have t in dB, so that's also log scale, but multiplied by 20. Then the first order low-pass filter, or what we call the low-pass single time constant transfer function, LP-STC, the Bode plot for the LP-STC would look like the blue curve that you see. So this omega 0 is the critical frequency, is the important frequency, the corner frequency, 3 dB frequency, half power frequency. This is the important frequency. Why is it important? Because here, around this point, around omega 0, things start to change. So before omega 0, the gain is almost constant at 20 log K. So K is the low frequency gain. And for frequencies much less than omega 0, the gain is almost constant, as you can see, at 20 log K. So K in dB. So this is for frequencies much less than omega 0. For frequencies that are much larger than omega 0, the gain will drop, and drop when I do log, when I do the Bode plot, dB versus omega log scale, the drop is a straight line. And it has a slope of minus 20 dB per decade. So when I go a decade, say from here to here, the gain will drop 10 times, or minus 20 dB on the dB scale. This minus 20 dB per decade is also equivalent to minus 6 dB per octave. Octave is a 2 times increase in frequency, 2x. So if I double the frequency, say from 10 omega 0 to 20 omega 0, that's not a decade, that's just doubling of frequency. I call this an octave. And then the gain will drop by minus 6 dB, not by minus 20 dB. Of course, the minus 6 and the minus 20 are related because the slope is the same. I'm dropping along the same line. So the slope can be expressed as minus 20 dB per decade or minus 6 dB per octave. So this is what happens for frequencies that are either much less here or much higher here than omega 0. Much less, I get almost constant gain at the low frequency value. So the frequencies that are much less than omega 0 are considered low frequencies, and the gain is almost constant there. For frequencies that are much higher than omega 0, much larger than omega 0, the gain drops with a slope of minus 20 dB per decade, or minus 6 dB per octave. Around omega 0, the gain drops from its low frequency value by 3 dB. So if the low frequency value is 40 dB, 20 log K is 40. At omega 0, the gain is 40 minus 3. So that's 37 dB. And that's why we call the frequency omega 0, we call the 3 dB frequency. Because if you take the transfer function and you solve what is magnitude of T at omega 0, you get T equals K divided by the square root of 1 plus omega 0 over omega 0, because omega is omega 0 at omega 0, right? So K over root 2. If you take 20 log of that, you get 20 log of K minus 20 log of square root of 2. So at omega 0, all of this is at omega 0. At omega 0, T, magnitude of T is magnitude of K over root 2. And in dB, it's 20 log K. So this value, this horizontal level, minus 20 log square root of 2. Now, 20 log square root of 2 is 3. So at omega 0, 20 log T is 20 log K minus 3. And this is where the 3 dB comes from. So 3 dB. At omega 0, the gain drops by 3 dB, and we call the frequency the 3 dB frequency. And then it continues and becomes a straight line with a negative slope. And another term we use for omega 0 is also corner frequency. And where does this come from? It comes from the fact that I can use asymptotes. I can do an asymptotic plot for the magnitude. So this is the first asymptote, just at 20 log K, a horizontal line, a straight line, horizontal, zero slope. And another asymptote, which is this, also a straight line, but with the negative slope of minus 20 dB per decade. And the two would meet, this line and this line. Where would they meet? They would meet exactly here at omega 0. So the corner where the two asymptotes meet is exactly at omega 0. And that's why we also call omega 0 the corner frequency. Okay, so 3 dB frequency, corner frequency, critical frequency. We also call it half power frequency because of this square root of 2. Because if you calculate the power, you take the voltage and you square it. So if you take the voltage and square it, the square root of 2 becomes 2. And the power becomes 1/2 what it was at low frequency. So again, at omega 0, the power at the output is 1/2 the value of the power that we get at low frequencies. And we call, therefore, omega 0 the half power frequency. So all of these terms refer to this important frequency called omega 0. And we see here how the gain in magnitude changes with the frequency, how we have two asymptotes, and how these two asymptotes, one of them is a horizontal level at the low frequency gain, and the other one has negative slope, which is minus 20 dB per decade. And these two lines, these two asymptotes, meet exactly at omega 0. The asymptotes can serve as an approximate Bode plot. So if I don't want to do the full curve, I can just use the asymptotes as an approximate Bode plot. But then at omega 0, there will be some error between the asymptotes and the actual curve, the blue one. And the error is 3 dB. And this is the maximum error between the approximate plot and the actual plot. The maximum error is 3 dB, and it's at omega 0. So for approximate, the asymptotes will tell me that at omega 0, I'm still at 20 log K. But in reality, I'm 3 dB below that. But otherwise, the blue and the asymptote here are very close to each other, and the error is very small. And then starting this point downwards, and the asymptotes and the actual blue curve are very close to each other, and the error is very small. So the asymptotes give a very good approximation. But at omega 0, we have to be careful that there is a difference of 3 dB between the two. Any questions about this material?